ID 192352821. My topic is Merkle Damgård construction. Now I am going to present it. So first of all, what is Merkle Damgård construction? So in cryptography, the Merkle Damgård construction or Merkle Damgård hash function is a method of building collision resistant cryptographic hash functions from collision resistant one-way compression functions. So what is collision resistance? In cryptography, collision resistance is a property of cryptographic hash functions. A hash function H is collision resistant if it is hard to find two inputs that hash to the same output. That is, two inputs A and B where A is not equals to B but H of A is equals to H of B. The pigeonhole principle means that any hash function with more inputs than outputs will necessarily have such collisions. The harder they are to find, the more cryptographically secure the hash function is. And what is one-way compression functions? So in cryptography, a one-way compression function is a function that transforms two fixed length inputs into a fixed length output. The transformation is one way, meaning that it is difficult given a particular output to compute inputs which compress to that output. One-way compression functions are not related to conventional data compression algorithms, which instead can be inverted exactly lossless compression or approximately lossy compression to the original data. The Merkle-Damgård hash function first applies an MD complement padding function to create an input whose size is multiple of a fixed number, example 512 or 1024. That is because compression functions can handle input of arbitrary size. The hash functions then breaks the result into blocks of fixed size and processes them one at a time with the compression function. Each time combining a block of the input with the output of the previous round. In order to make the construction secure, Merkle and Damgård proposed that messages can be padded with a padding that encodes the length of the original message. This is called length padding or Merkle-Damgård strengthening. The Merkle-Damgård construction was described in Ralph Merkle's PhD thesis in 1979. Ralph Merkle and Ivan Damgård independently proved that the structure is sound, that is, an appropriate padding scheme is used and the compression function is collision resistant. Then the hash function will also be collision resistant. This construction was used in the design of many popular hash algorithms such as MD5, SHA-1 and SHA-2. So, what are the security characteristics? Second preimage attacks against long messages are always much more efficient than brute force. Multi-collisions, many messages with the same hash can be found with only a little more work than collisions. Harding attacks, which combines the cascaded construction for multi-collision finding similar to the above with collision find for a given prefix, chosen prefix collisions that allows for constructing highly specific colliding documents. And it can be done for more work than finding a collision, but much less than would be expected to do this for a random oracle. Length extension attacks were actually used to attack a number of commercial web message authentication schemes, such as one used by Flickr. Now, wide pipe construction. Due to several structural weaknesses of Merkle-Damgård construction, especially the length extension problem and multi-collision attacks, Stefan Lux proposed the use of the wide pipe hash instead of Merkle-Damgård construction. The wide pipe hash is very similar to the Merkle-Damgård construction but has a larger internal state size, meaning that the bit length that is internally used is larger than the output bit length. If a hash of n bit is desired, the compression function f takes 2n bits of changing value and m bits of the message and compresses this to an output of 2n bits. Therefore, in a final step, a second compression function compresses the last internal hash value 2n bit to the final hash value n bit. This can be done as simply as discarding half of the last 2n bit output. SHA-512 224 and SHA-512 256 take this form from since they are derived from the variant of SHA-512 and SHA-384 and SHA-224 are similarly derived from SHA-512 and SHA-256 respectively, but the void of their pipe is much less than 2n. Now, fast wide pipe construction. It has been demonstrated by Mridul Nandi and Saurabh Dutipal that the wide pipe hash function can be made approximately twice as fast if the wide pipe state can be derived in half in the following manner. One half is input to the succeeding compression function, while the other half is combined with the output of that compression function. The main idea of the hash construction is to forward half of the previous chaining value forward to XOR it to the output of the compression function. In so doing, the construction takes in longer messages block every iteration than the original wide pipe. Using the same function f as before, it takes n bit chaining values and n plus m bits of the message. However, the price to pay is the extra memory used in the construction for feed forward. The length padding example. To be able to feed the message to the compression function, the last block needs to be padded with constant data, generally with zeros, to a full block. For example, suppose the message to be hashed is hash input, which is a 9-octet string, and the block size of the compression function is 8 bytes or 64 bits. We get two blocks, the padding octets shown in the light blue background color. This implies that other messages having the same content but ending with additional zeros at the end will result in the same hash value. In the above example, another almost identical message will generate the same hash value as the original message hash input above. In other words, any message having extra zeros at the end makes it indistinguishable with one without them. To prevent this situation, the first bit of the first padding octet is changed to 1. To make it resistant against length extension attack, the message length is added in an extra block at the end. However, most common implementation uses a fixed bit, generally 64 or 128 bits in modern algorithms, at a fixed position at the end of the last block for inserting the message length value. Further improvement can be made by inserting length value in the last block if there is enough space. Doing so avoids having an extra block for the message length. If we assume the length value is encoded on 5 bytes, the message becomes 48, 61, 73, 68, 49, 6E 70, 75, 74, 80 and 0000000009. Note that the storing the message length out of the band in metadata or otherwise embedded at the state of the message is an effective migration of the length extension attack, as long as invalidation of the either message length and the checksum are both considered failure of integrity checking.